Presentation on the atom, and it's on what's on the outside that counts. It says true terror is to wake up one morning and discover that your high school class is running the country by Kurt Vonnegut. So the learning goals for this particular presentation are that you be able to identify the number of valence electrons in an atom, and you use the valence electrons to predict the properties of an atom. So here's what we already know. We already know that the identity and properties of an atom are determined by the protons, neutrons, and electrons. And we also know that electrons are on the outside of the atom, where you have an atom with a nucleus, and then surrounding it you have electrons that are in orbitals. Now hopefully in the lab what you learned was that the electrons are put into electron orbitals, and that the energy levels can hold different number of electrons. So this first one can hold 2, and the second one can hold 8, and so on and so on and so on. And we also learned that the outermost level is referred to as the valence shell. So for example, in this one, the second shell is referred to as the valence shell. If I were to add a third one, then this one would be referred to as the valence shell. The outermost level is referred to as the valence shell. So, electron orbitals and energy levels. Each energy level can hold a different number of atoms. So the first thing that we realize is that the first one, this is represented by this K, can hold 2 electrons. So the first orbital can hold 2 electrons. The second one is referencing the 2 L's. They can hold a total of 8 electrons. Then we have the M's, they can hold 18. And then the next one, if you keep going, can hold even more. It can hold up to 32 electrons in each. Okay, at this point, this is the number of electrons that you can use. Now we're going to stick to, for the most part, the 2, 8, and 18. Although if you do get into the fourth orbital, it can hold a lot more electrons. So now we need to talk about the difference of inner electrons versus outer electrons. Valence electrons are referred to as the outermost level, while the inner electrons are referred to as shielding electrons. Okay, they're referred to as shielding electrons because the outer electrons don't get to feel the full positive charge of the nucleus because all these charges are in the way. That's why they're called shielding electrons, and that's something that you may explore later in another chemistry class, but for now we're just going to call them shielding electrons. The valence electrons are the ones that are on the outermost level. So if you look, this drawing that we have here has one valence electron because it only has one electron in the valence shell. The properties of atoms are determined by the valence electron structure. Calcium has 2 valence electrons and barium has 2 valence electrons. If you look at them, they've got all these other electrons, but what it comes down to is you have 2 electrons in the valence shell and you have 2 electrons in the valence shell. What that means is that calcium and barium are very, very similar in how they react. Because their valence structure is the same, they tend to react the same to form new compounds. They have the same reactivity with water. They form acids and bases the same way. All the reactivity tends to be the exact same because they have the same valence structure. In addition to that, calcium and barium are both in group 2 on the periodic table. Everything in group 2 has 2 valence electrons. In fact, there's a nice little pattern for the periodic table. If you were to look at group 1, and group 1 is the first column. We're talking about columns here, not rows. Columns go up and down. Everything in the first column, like hydrogen, lithium, potassium, sodium, got those out of order, sodium and then potassium, they all have a single valence electron. Everything in group 2, like calcium and barium, like we talked about, has 2 valence electrons. Then we skip the middle. We skip 3 through 10, and we come here to group 13. Everything in group 13 has 3 valence electrons. Everything in 14 has 4 valence electrons. Everything in 15 has 5. Everything in 16 has 6. Everything in 17 has 7. And everything in 18 has 8 valence electrons. So you can predict the number of valence electrons for any atom so long as it's not in this middle section right here. That middle section is something that we're going to ignore for now because it doesn't follow a consistent pattern. What determines if an electron is a valence electron? It determines if it is in the outside energy level. If it's in the outside energy level, then it's a valence electron. Okay, how many electrons can an atom hold if it contains only the first, second, and third energy level? Remember, the first energy level can hold 2, the second energy level can hold 8, and the third energy level can hold 18, which means that you have a total here of 28 electrons. Next, this is how many electrons does selenium have? So you need to take your periodic table, and you find selenium, and you figure out where selenium is on the periodic table. You look at the column that's associated with selenium, and then you remember, okay, If it's group 1 or group 2, it's got 1 valence electron or 2 valence electrons. If it's 13, it's got 3 valence electrons. 14 has 4 valence electrons. And then I will leave that to you to go ahead and figure out what it is for selenium. Okay, it says the element below gains 2 electrons. Write the nuclear symbol notation and determine the number of valence electrons. So if you were to look right here, the first thing we do is we say, okay, if I'm writing it in nuclear symbol notation, I know it has an atomic mass of 19 because that's the number of protons and the neutrons. We know that it has a atomic number of 9, so that's going to make it fluorine. Now, as it's drawn, we know that it has 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So right now it's neutral, but it says it gains 2 electrons. So what I'm going to do is I'm going to add another electron to it. When I add another electron to it, now it's got 8. So remember 2 and 8, it has to add another shell. When you add that other shell, you can only put 1 electron in there. So what you would do is you would say 2 minus, because it has 2 more electrons than protons, and then you would say that it has 1 valence electron. That is a really, really tough example. Now, we can also draw what are called Lewis dot diagrams. Chemists draw the valence structure around an atom. So whenever I draw lithium, I put a single dot in there, even though lithium has 3 electrons. Because the 2 electrons, if we draw lithium, the 2 electrons are in the inner shell, or the shielding, and then you have 1 valence electron. So the Lewis dot diagram is representing the valence electrons only. So lithium is in group 1, so it has 1 valence electron. Beryllium is in group 2, so it has 2 valence electrons. Boron is in group 13, so it has 3 valence electrons. Carbon is in group 14, so it has 4 valence electrons. Now, one of the things that you'll see that we like to do here is we like to pair the first set of electrons up. Now there's a reason for that. It has to do with s and p orbitals, and it's kind of confusing for now. But we like to get you in the habit of putting the first 2 electrons together and then spreading the rest of the electrons around the atom to get as far away as possible. So if you look, we put the 2 electrons for boron together, and then we have another one that's to the side. We put the 2 electrons for carbon together, and then we put the other 2 on the other sides. Okay, notice how these aren't paired up. Okay, the only ones that pair up are the first 2, and there's a reason for that that you guys will explore more in chemistry. But for now, like we said, we just want you to get in the habit of it. Okay, fundamental B1, it says what type of electrons should be used when drawing a Lewis dot diagram. Remember, the only ones that matter are the valence electrons. That's what this entire presentation is about. Next, it says a new element is discovered with the Lewis dot structure. How many valence electrons does XYZ have? Remember, Lewis dot structure is telling you the valence electrons. So if you were to take a look at this, it has 2, 4, 5, 6, or 6 valence electrons. That also means that it would belong to group 16, which is where oxygen is. Next it says draw the Lewis dot structure for nitrogen. So the first thing we do is we write nitrogen, and now we need to figure out how many valence electrons nitrogen has. So remember, when we draw nitrogen, the first thing is we can put 2 electrons on the first orbital, and remember I can put 8 in the second one if I need to. So I go 1, 2, 3, 4, 5, and if you look at that point, I'm added up to 7 electrons, so I'm good. Some of you may have said, well, why didn't I just look and say nitrogen is in group 15 so that there's 5 valence electrons? That's another way of doing it, and that's perfectly valid. So remember, I put the first 2 electrons together, and then I put the next one, the next one, and the next one, and I separate them out. So this is the valence structure for nitrogen. Group 18 is often referred to as the noble gases because they do not interact with other substances. It says draw all of the electrons for neon and speculate as to why. Okay, if you were to look at neon, neon has 1, 2, and then it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 valence electrons. Now remember, the neon can hold 2 electrons in the first shell. It can hold 8 electrons in the second shell. And if you look, neon has a completely full orbital shell. It satisfies what is called the octet rule. Okay, most atoms are stable whenever they have 8 valence electrons. Okay, that's why everything that's in the noble gas category, that last column on the periodic table, has 8 valence electrons. They're noble gases because they are stable the way they are. So neon is a noble gas because it doesn't want any more electrons. It doesn't want to lose any electrons. It is perfectly stable the way that it is. And that will have an important part when we talk about chemical bonding in future units.